This is lecture 4E for Calculus 1 on optimization. Optimization refers to usually finding the maximum or minimum of some parameter. For example, you might want the maximum profit, or the minimum cost, or the maximum length, or the minimum distance between 2 points. So there's usually a procedure for finding this. The middle step is usually the problematic one. Okay, the first steps are, if at all possible, make a sketch of the situation. I've only said that a million times, so now you know it. Okay, make a sketch, and okay, say sometimes the problem is half solved when you've made that sketch. Okay, having made the sketch, write the main equation for the situation. Decide what you want to minimize. Is it profit? Is it area? Is it distance? And write that equation out in terms of your situation, in terms of the sketch you made. Now, what will happen now? Here is the big problem. Once you write this main equation, you will see it depends on several variables. That is too much. You need that area to depend only on one variable, or the length to depend on one variable, or the distance to depend on one variable, because then you can use this calculus to solve it. If you have area depending on 3 or 4 variables, you end up with that situation like bumps in a rug. You know, you push down one and it comes up somewhere else. Okay, so you want to use other information in the problem and let that supply a constraint on some of the variables so you can rewrite the equation. So I'll show you, I'll give you some examples on how to do it. Okay, say your problem is to rope off the largest rectangular area that you can with a certain amount of rope. So of course that's pretty easy. You can sketch a situation here. Get the line straight. Okay. And this is of course trivial. And something here is the width, and over here is your length. Okay, fine. Now you need to write the main equation. The main equation is area equals length times width. Alright, you've got the area depending on 2 variables, length and width. You need to eliminate one of them. Right? So say you have a certain amount of rope. That will be your constraint. And the amount of rope is what's going to go all around the outside of this rectangle, so that is the perimeter. And I know the perimeter equals twice the length plus width. Now I can use this constraint equation to write everything in terms of length only. From the constraint, I can find a value for the width. Remember, p is just going to be a constant to supply later. So width is now in terms of length. I substitute that into the equation, and now I have area in terms of length only. I will then take the derivative of area with respect to length. The other thing to point out, which I pointed out a zillion and a half times, is that when you're faced with a problem like this and somebody says you have to use 100 feet of rope, just use P. Later on, they'll ask you to find it for 500 feet of rope, and you'll have to redo the whole problem. But if you solve it with P, a general perimeter, then if somebody says 250 feet of rope, you can just put the 250 in and you're done. Okay, so those are just sort of, I don't know, style points in solving optimization problems. Okay, so here's what we did. We did a sketch, we wrote down the main equation. Then we found some kind of constraint that would eliminate those 2 variables, so we only had one, or eliminate one variable. We used the constraint to write width in terms of length. We substituted that into the equation. Now I have area in terms of length only, remembering that P is just a number to be supplied later. Okay, here's another one that's a little harder. This was in the book. You see it in most calculus books. You see it in trig books as well. So you have a corner, and on one side of the corner you've got a 9-foot hallway. On the other side of the corner you've got another hallway that's 6 feet. Right now we'll leave them as 9 and 6 just to get on with the problem. You can see how you would write them in general. And the idea was, what is the biggest ladder you can carry around this corner? Alright, so here is the problem, and now we've done a sketch, or somebody did a sketch for us, and I added some little scribbles on it. What you can say is that this whole length of ladder is going to have 2 sections. One section that's sitting over here in the 9-foot hallway, one section that's over in the 6-foot hallway. So I'll break the ladder up into 2 sections, L1 plus L2. Fine, but now I have the ladder depending on 2 variables, L1 and L2. So if I look again, now you're going to use trig. I could say that if I look over here, the sine of theta is 9 over L1. This is a 9-foot hallway, so it's 9 feet, right, like in that dimension. Okay, over here, that is the same angle. This is where we're going to get one parameter. And the cosine of that angle is 6 over L2. So now I could write L1 equals 9 over sine theta, and L2 equals 6 over cosine theta. Substituting that for L1 and L2, I now have the length in terms of angle only. So I can take the derivative of L with respect to angle, find out where that's minimum, then go back, find my L1, find my L2 from these equations, and then find the whole length of the ladder. So you see that middle part is hard. You might not have recognized that right away, and many people don't. But once you start seeing these, you realize where the difficulty is. The difficulty is taking that main equation and somehow reducing it to an equation of only one variable. And here's a third example. This is the rain gutter problem that I will do in one of the next lectures. So here's a rain gutter problem. You have a 30 centimeter piece of metal, assume it's aluminum, so you can bend it pretty easy, and you want to bend up both sides of it to create a rain gutter. So it's going to carry, let me get the marker here, it's going to carry water in here. Alright? And the idea is, what should you do with the sides? Should you bend them straight up so you have a rectangular rain gutter, or should they be slanted out to the side? You know how to do that. Alright, so the idea is you want to maximize the area inside the rain gutter. So the area inside the rain gutter consists of two parts, the rectangular part in the middle and these two triangles on the outside. I have to draw in this sketch what h is. H is the height right here. Okay, so that's your height. Put an h there for it. So there's height, and the base of these triangles is B. Right, that makes sense. You have the area of the rectangular section in the middle. Of course, this is also the same height, so you see that makes your rectangle in the middle. We're assuming you bend them up equally. Whoops. You bend them up equally on both sides. You know, you don't bend up one side halfway and leave the other flat. Right. So you can see the rectangular section in the middle is, the area is 10 times h, and the two triangles, the area is 1/2 bh. Right. So now you have the area depending upon the base of the triangle and that height. Actually, both of them are rather difficult to measure. That's two variables. You want to get it down so area depends on one variable only. And here's how this is done. You look at the area, that angle that you're bending things up at, and you find out that you can write the sine of the angle is the height over 10. Remember, 10 is hypotenuse. And the cosine of the angle is, that should be a b right there. I'm going to correct it. Well, let's see what we can do for that. All right, is b over 10. All right, that's pretty bad. So we'll try it again. It's b divided by 10. The important thing here is, remember, you did a sketch. In this case, someone did it for us. You do the sketch. You write the main equation. You see you got too many variables. You look back at the sketch or look at your other information and say, what constraint is there that's going to allow me to eliminate these variables and end up with the area depending on only one variable. Trig identities are frequently used. Pythagorean theorem is used, and algebra is used. Okay, well, the drawing got erased, but I think you can half remember it. And now I make these substitutions, so I can write h in terms of sine theta and 10, and again that was a b. I can write b in terms of cosine theta and 10. I substitute that all into my equation, and here's what I get. A equals 100 times sine theta plus sine theta cosine theta. Alright? The area totally depends on theta. Now I can take the derivative with respect to theta and find the angle that will give me the maximum area for the rain gutter. Okay, once you have done that, and like I said, that is a critical problem. That's what's going to hang you up. Once you have the area, the distance, the length, the cost, whatever, in terms of one variable, take the first derivative and find the critical point. Critical point would be the point where that derivative is 0. All right, and that would be a suspected local maximum or local minimum. You don't know whether it's a maximum or minimum, so you take the second derivative. If the second derivative is negative, the point is a maximum. If the second derivative is positive, it's a minimum. And basically, that's all there is to it with the calculus. Of course, there are pathological problems all over the place, and in math we make you do these pathological problems and find all these inconsistencies, but by and large, it's pretty straightforward. Once you've written the equation, once you've done the sketch, written the equation, simplified down to one variable, then just take two derivatives, evaluate them, and you're pretty close to having a solution. You should have a solution, except in some pathological cases. The next 4 lectures, I'm going to do 4 problems. I think 3 of them are from business, and one of them is the rain gutter problem.